Cole and I were asked to lead a discussion on the products of mass transfer. And then the title in the agenda became the astroseismic signatures of mass transfer. And so now this is a bit of a two-parter that's going to cover both of those. And we're going to start off with Amadeusz giving a short overview of some recent work he's done on the astroseismic signatures of mass transfer for main sequence stars. So over to Amadeusz.
Yeah, thank you, Simon. Let me just see if this works. No, oh yeah, it does. All right, so as a first, I would like to talk very briefly about one of my findings with my supervisor during my PhD. So we've studied two binary systems, two post-mass transfer binary system. So KIC, this ridiculously long number, and ABCAS. Both of them are actually systems with AF-type stars with primary stars around 2-ish solar masses and secondary stars 0.2 and 0.4 respectively. In case of KIC system, the primary is gamma delta Scurry hybrid pulsator, whereas during in ABCAS we have a radial mode pulsations on the primary star. So we performed a complex binary modeling in each case, try to fit models both to observational data, orbital and physical parameters, and as well as pulsation frequencies. What we found is that slightly non-conservative mass transfer was needed in order to get a right model that would recreate our system in a current condition. But we also found that the mass transfer can actually lead to the helium enrichment in the outer layer of mass accreting stars. And actually that last comment has a profound impact when it comes to studying pulsations of mass accreting stars. In a case of KIC system, I don't know, do we have like, okay, maybe I'll just operate with my mouse. Yeah, I've told you about that helium enrichment, and even though that helium enrichment, which is shown on the right-hand side panel, the top of that, is not enormous, it is sufficient enough to extend the driving zone for the pulsations that are happening in delta Scurry stars. So basically, delta Scurry pulsations are driven in second ionization of helium sphere, or not sphere, in region of second ionization helium. So if we add additional helium to that region, then basically excitation of oscillations overcomes the damping mechanisms. And we can actually see not only P modes being excited, but also G modes, which is actually one of the first findings in delta Scurry's modeling. In case of ABCAS, where we had a previous mass transfer obviously changes your initial structure of a star and adds some fresh material on the top, and by that it affects your dynamical frequency, dynamical timescale in which, in terms of radial pulsations, the star pulsates, and basically changes the evolution of the frequency during the time. So on the left-hand side panel, we have a comparison between HR diagram on the top and how in terms of a function of logarithmic temperature, the frequency actually evolves. So at first, what we would like to have when it comes to comparing to like normal conditions in single stars, during the evolution of a star in main sequence, the frequency of a radial mode basically drop all the way up to the exhaustion of hydrogen in a core. But what we actually have here is that the reversal of the evolution, and in fact giving us few crossings of observed frequencies during the main sequence phase. So how does it look like when it comes to comparison on the HI diagram, except for only one, like, constant frequency line, when it comes only to singular case of stellar evolution, we actually end up with a couple of crossings and couple of constant frequencies line during the main sequence. So with that, I'd like to conclude, and Matthew, the floor is yours.
Yeah. So I'm gonna pretend to be Cole and present you work from Tom Wag. Cole was the primary supervisor, and I put this together like literally in the past 2 minutes. Tom also investigated in a similar way as Amadeusz had done just before us, the impacts of accretion on the astroseismic signatures of SPB stars. So these are in the 3 to 5 solar mass range, right? Something like that. So this plot here is showing you what rejuvenation is, which probably many here are familiar, but it shows the hydrogen mass fraction as a function of mass coordinate. And if you look at the axis, it's really focused on the mass coordinate at the edge of the core of this star. And the colors mark the passage of time from light to dark. So you start with this pink curve here, which has a normal slope. Okay, that's the main sequence core receding because you're turning hydrogen into helium. But then as the colors get darker, you see that this boundary gets steeper and moves outward. Is the convective core of the star that is growing because the mass of the star is changing. But the important thing here is that this core envelope boundary, here I'm showing it with the hydrogen abundance, but you can imagine to plot the density, to plot any other property, they will also get steeper and move further out. And since G modes can probe this area of the star, we expect to see some signature when we predict different, the pulsations of this star. And in particular, Tom looked at, is this working? Yes. Tom looked at the periodogram for these stars. So this is, and I'm gonna butcher this, but this is the period spacing of adjacent mode, G modes of the same N and adjacent Ls, right? Is that correct? Or yeah, as a function of the period of the mode itself. It really doesn't matter the details for the point that I want to make. It's 2 curves, 1 per each star. They are different because we are looking at 0-age main sequence stars. Central abundance of hydrogen is the initial one. And these stars have different masses right now. The orange one is a single 3.5 solar mass star. The purple is right now 3 solar masses. And then Tom is gonna make it evolve and dump 0.5 solar masses on it until they become the same mass. And before that, like this was, okay, this is curves at 0-age main sequence. So the star is fully homogeneous. Then as the stars evolve, you see structure appearing in these plots. This is the core forming, changing its composition and imprinting a structure here. But the curves are very different still because they're still different masses. And then I think at this point, yes, I think at this point, instead, this is post-accretion. So you see that now the median line here, they align very well. This is because now the stars have finally the same mass by construction. But you see that the points are different. There is a difference here in this periodogram. And this difference persists for the remaining main sequence evolution of the accretor. Not only persists, but one could even argue it grows and becomes more structured. And you can see, for example, that there are some modes that are like exactly, where are they? They're exactly in phase, and some modes that are kind of in anti-phase. And this is because different modes have different sensitivities to different regions of the star. And so this is a proof of concept exercise where we did a simplified binary model where we stopped the accretion. There's no rotation involved here, but it shows us that it's reasonable to expect that we have differences in the asteroseismic signatures even without changes in composition. Like here, we didn't dump more helium on the surface of the star. This is just the structure that changed to readapt to the new mass. And one quick thing that I want to highlight is that this rejuvenation thing may also matter for the rest of the evolution. You change the core envelope boundary, so you changed where most of the mass of the envelope is, the deepest point of the envelope. And this has a significant impact on the binding energy of these accretors. So this plot is showing you as a function of radius in the star, the ratio of a binding energy of an accretor star versus a single star of the same mass. And you can see that for most of the volume of the star, the accretor has a lower binding energy. And as the radius of the accretor increases, so as the accretor evolves, this gets bigger. That's because this effect of the rejuvenation is then amplified by the evolutionary contraction of the core of the accretor. And yeah, that's kind of go back to your side.
I think, Simon, you're going to jump in?
Yeah, sure. Thanks, Matthew. Yeah, I think the conclusion there is that although those changes are subtle, that with experience, with a trained eye, you can pick them apart and you can learn a lot about the signatures of mass transfer. So if you want to cancel the screen share, Amadeus, I'll
Sure.
jump in. I think that might be a little easier. All right.
No.
No.
That
Yeah, we see
works.
it.
That works. No, sorry, we said no to someone. Okay. Your screen share works.
My screen share did work?
Yeah, it did,
Your
it
screen
did.
share did work, yes.
Yes.
Okay. I
Multiple
think
conversations going on.
Do we see your screen now? You just
Yeah,
put the
okay,
slides
great.
through.
Thank you. All right, here we go. Cool. So I was going to talk about the astroseismic signatures of mass transfer in red giants. This sort of arose as a question in a discussion yesterday, so I thought I'd share a little bit about this. So one thing to note is that even in single stars, you lose 0.1 to 0.2 solar masses on the red giant branch through the combination of pulsations and winds. So there is always going to be a little bit of mass loss. Now, if an RGB star loses its entire envelope through Roche lobe overflow or some other mechanism, then it becomes a hot subdual. There's nothing new there. But if the red giant star only loses part of its envelope, it's actually almost indistinguishable from a single red giant branch star based on the surface properties alone. So if you're just looking, say, at effective temperature and surface gravity, it's extremely difficult to distinguish single red giant branch stars versus those that are in binaries that have lost a little bit of their envelopes. But from astroseismology, you can actually determine they have different core masses and that a mass transfer episode has occurred, and you can roughly estimate how much mass they have lost, especially if you can measure some properties of the binary system. And then Yaguang Li's work also showed some superficially single RGB stars with masses less than 0.5 solar masses. And that just isn't possible at the current age of the universe unless that star lost some mass somewhere along the process. And so here's a figure of what that looks like. Just showing mass versus metallicity here for a very large number of Kepler red giant branch stars. And there's a whole bunch of stars in blue off the left-hand side here that at greater than 1 sigma have masses that are far too low. These stars could not have evolved as single stars within the current age of the universe. I forget the exact number, but there were sort of dozens of those stars. And then in red here are, I think it's 7 red giants that have measurably different core masses from what you would expect if they were single stars. So that's also an astroseismic identification. So that just sort of addresses that query that came up yesterday about whether you can detect whether red giant branch stars have transferred mass or whether they've evolved as single stars. Something that I've worked on in the past is pulsation timing as a probe of mass transfer, because with pulsation timing, you can determine orbits for lots of stars. And I'd just like to talk a little bit through this period and eccentricity diagram that arises from pulsation timing of many orbits. So this is compiled from 341 pulsation timing binaries. These all have A-type primaries. They're delta Scuti stars, so they have masses between about 1.5 and 2 solar masses. This sample is complete periods between about 100 and 1500 days. So it's incomplete in these areas that are sort of shaded in dark gray here. So we don't include those dark gray regions in our statistics. What you expect is that at shorter periods and higher eccentricities, so up here in the diagram, you must have main sequence plus main sequence pairs. If either of these stars had become a red giant at some point, then these systems would have rapidly circularized and moved to very short periods. So they would be off the lower left of the diagram. At the bottom of the diagram, these systems could have had mass transfer without necessarily resulting in very short period systems. And so what we observe is this pileup down here of these long period, low eccentricity systems, and they all have mass ratios, well, not all of them, but most of them have mass ratios very close to sort of 0.3. And so with primary masses of about, say, 1.7 solar masses, that gives you companion masses of about 0.5 or 0.6 solar masses, which is quite typical for a helium white dwarf. And so to answer the question of what are the products of mass transfer, these are basically white dwarfs that have decayed towards low eccentricities. And in fact, that we find that 21 plus or minus 6% of binaries that have A-type primaries, so delta Scuti primaries, they have white dwarf companions in this period range. And this is a measured number. It's not model dependent. It's not based on a population synthesis model. The only models that we use are just some MCMC type algorithms to discern this fraction. The donors could have been AGB or RGB stars. So it depends whether the mass transfer happens at the tip of the RGB or if it happens after the red clump phase when the stars are on the asymptotic giant branch. And interestingly, some of these companions appear to be very massive, so as high as 1.4 solar masses. And our most massive companion of this type has no luminous contribution to the spectrum. So if you take just a normal spectrum of this system, you see the delta Scuti component, you see a main sequence A star with about 1.7 solar masses, and you see no other contribution. This is not an SB2 system. And that's basically ruled out at, say, the 5% flux level or even less, which means you can't even have a triple system where you have 2 companions of 0.7 solar masses instead. And so this companion has to either be a white dwarf very close to the Chandrasekhar limit, or it's already become a low mass neutron star, and in future it will be an accreting neutron star when the delta Scuti star ultimately becomes a red giant. So this could be a type 1a progenitor, or it could be a future accreting neutron star. Also earlier in the week, we were discussing a little bit, when do pulsations matter? And one of the things I argued largely via Slack was that pulsation velocities are actually a good proxy for changes in radius or log g, but perhaps we need to reparameterize them. So maybe we need to look at the radius of the star divided by the dynamical timescale, or maybe we need to look at the Roche lobe versus the orbital period. But when and or where are the pulsations significant enough that they need to be included in models of mass transfer? Certainly it's not for FGK dwarfs. Those only have amplitudes of tens of centimeters per second. Their pulsations are not significant as far as mass transfer models go. I also argued that for spectral type B or A dwarfs, although the amplitudes are only a few kilometers per second, you get gravity modes in these stars These can be coupled to tides. They can be tidally excited G modes, in other words, and those are very important. And we saw that in the talk on Monday. For stars on the red giant branch or in the red clump, the amplitudes can be up to 1 kilometer per second. On the red clump, that's probably not significant because there's no substantive change in radius happening. But at the tip of the red giant branch, this radius is continuing to expand. And so those pulsation amplitudes could be significant in mass transfer models. And then, of course, we have the asymptotic giant branch phase where the thermal pulses are highly significant, as we all know. So to move this to the discussion, I have posted 4 questions here. I'm hoping that everyone can sort of self-organize into groups and that Amadeusz can help facilitate that in person because I'm obviously not in the room. And so here are the 4 questions. I don't know if it really adds anything for me to read these out, but there is a editable slide deck for your answers. I'll copy that link into the Slack if it's not there already. And so if you just like to divide up, or maybe I should just hand back over to Amadeusz now and he can facilitate that.
Oh, I think the neat idea to be, because we are not in that number as we were yesterday and 2 days before. So 4 questions should be enough to divide ourselves into 4 groups. Maybe Simon, could you please post those questions on Slack, and following one of the ideas that was said on Monday, I guess, like post some emoji right next to each of that, and people who will react according to such emoji they've chose will actually build up a group, and then we could divide ourselves and try to answer and address those questions.
How long do you want to take for addressing, and how much do you want to take time to reconvene?
Simon?
Because
Yeah,
we
I
have
think that's a
about
good
half
idea.
an hour.
So we have half an hour until the lunch break. So perhaps do we think 20 minutes for discussion and 10 minutes for a wrap up is the best way to go here?
Can we just discuss the question in the room?
We can also just discuss the question in the room and we don't have to break out. It might be faster.
Sure.
Oh, yeah, I like that idea. Yeah.
And we're the smaller group in the room anyway, so. We're already a breakout group.
Okay, cool. I can't see that from the Zoom, but yeah, the attrition is noticeable.
About
but...
half that it was yesterday, I think. Oh, so we're still half.
Put the questions back up.
Yep,
Can the
yeah.
questions be shared again? Yeah. And, I will walk around.
Yeah, I'll share it, Simon.
Oh, you're doing it? Okay, yeah, great. I was just good. Thank you.
Are there any volunteers who want to help with more mic running? I think it'd be nice. Tomer, you had a question already? Are we gonna go one
You can even
over?
pass around this one.
Walk around.
Should I ask a question? So about the pulsations, and you showed actually that there are differences between mergers and non-mergers in terms of the pulsation patterns, whatever the assumptions are there. But I'm wondering is whether these differences are unique or whether you could get them in other ways, like playing with mixing, playing with abundance pattern, playing with the age.
I think I can answer that. So we didn't try to do a full systematic exploration. So the answer that I can give is tentative. This is a valid question to explore better. But I didn't show this, but if you look at the Brunt-Väisälä profile of the models, they are really qualitatively different in the sense that a single star, the core will only contract and get smaller, and this leaves a smooth Brunt-Väisälä profile. While in an accretor, because of the rejuvenation pushing out the core, you can get a double peaked Brunt-Väisälä profile. And I cannot think of a process that would make that in a single star. Now, changing, overshooting, you would change the slope of those things, so you wouldn't change the signals, but the fact the difference is there should be robust against that, is my hunch.
Yeah, the only way I can think of doing that would be to like change overshoot, change it back, change overshoot, these kinds of very contrived
And then
engineering
mimicked
tricks.
what the binary is doing in a sense. Right?
Exactly.
Can I follow up on this? Actually, I'm wondering, so I'm from the high mass stars, and as far as I know, none of this has ever been observed. So yesterday we briefly touched upon why, or if there is any observations of objects that we think are merger products and whether we could test it. And for the low mass stars, I have no idea. So the question is basically, can this or has this been done for lower mass stars? And are there any chances of doing this for any of these high mass merger candidates?
I think Zettelfuki. And actually, Dominic Bowman has secured 4 nights on Espresso to do astroseismology from spectroscopy, so high cadence, high resolution, high signal to noise spectra. And we're going to try, like the models that I showed here were toy models with no rotation, with homogeneous chemical composition. We're going to try to do the same kind of analysis with our models for Zettelfuki that account for all of these effects in however way you can. And we're gonna try to get the data, and Zettelfuki is the nearest O-type star to Earth. So if we cannot with that one, I think then it's hopeless. But we are gonna try with Zettelfuki. I don't know about the lower mass stars though.
I don't know about the observational content part. Maybe not.
But you see.
Mergers or just any mass
Well,
transfer?
I mean, Zeta is not supposed to be merged.
No, it's an accretor. Zettelf is an accretor, but similar effects will occur in mergers, right?
Yeah, so I'm thinking about Rui and Fuller from a couple of years ago that has like 24-ish candidates that had weird core masses for their envelope masses detected seismically that they interpreted as merger products. I don't know much more about that, but these like 2 solar masses or less.
I think in that case, what they did with their model is just they constructed weird core envelope mass ratios, which also changes these. But yeah, they have, well, how many candidates you said? 25?
24. I'm just looking at the abstract right now.
I have a mic though. You don't need to go. Whoa. So one question, I'm kind of looking at question 1, and Sylvia and I have been having a little bit of a like side conversation about features in the orbital period distributions of post common envelope and post stable mass transfer white dwarf main sequence binaries. And so there's a few of these data sets, like Amanda talked about the AGGC from Apogee. There are some post-common envelope binaries from SDSS that have like M-dwarf companions. And there's all of these different features that are showing up in the orbital period distribution that seem to change in the different data sets. So there's gaps that open up at different parts of the orbital period space for the different data sets. And one thing that I'm curious about is one thing that's tough with the AGGC is that it's not a super narrow mass range, but I'm wondering if there is a potential for using things like astroseismology as a like distinct window into specific mass ranges or spectral types when we get really large data sets from like Gaia and
Can
DR4.
you explain which gaps? Did you say there's gaps? What
Just like there's like peaks at orbital. So like the so in the AGGC, we see a bunch of systems that peak in something like 10 to a couple hundred days, and then there's a drop that is definitely not due to like a 1-year cadence thing like you would see in Apogee, or sorry, in Gaia. So there's just, it's like things drop off and then come back at higher periods, at least in the AGGC, and then in the SDSS post-common envelope binaries, things seem to really like drop at, what did you say, Sylvia, like 8 days?
Yeah, I think like it peaks at 5, 6, and then there's hardly anything
Yeah,
after.
peaks at 5 or 6 days and then drops at 8
But-
and then comes back.
No, they're not sensitive to further than 50 days.
Oh, but they're
Only have like a lower mass.
So the SCSS sample, they're not sensitive to orbits wider than 50 or 30 days. So they see this cutoff at low periods, say like a couple of days, and then just nothing afterwards. But if there's something popping up at 100 days, they wouldn't be able to say.
So, and I guess that kind of illustrates the struggle of trying to go across these different surveys. It's really difficult to understand the survey selection. And so I'm curious if there's ways that we could be cross-cutting in astroseismology to at least help with things like mass estimates.
So I can speak to that a little bit with the white dwarfs and the opportunities for pulsation timing there. Because a lot of white dwarfs also pulsate. It just happens that their pulsations are not very good clocks. The pulsations sort of have intrinsic phase shifts that we don't fully understand. And so unfortunately, pulsation timing on white dwarfs doesn't work particularly well. However, if you have a large enough sample of them and they pulsate in enough modes, then maybe you can just sort of crunch this out in the numbers and you get away with it. Then it would depend on how good are the light curves that we have for these white dwarfs, which also probably depends a lot on how bright they are.
I was also thinking companions to the white dwarfs.
So like the main sequence companions to them?
Yeah, yeah.
Yeah, okay. Again, it depends on the quality of the light curves. Doing astroseismology on main sequence solar-like oscillators, if they're sort of G or M, if they're K or M dwarfs, is extremely challenging. If they're G dwarfs, you can do it. You know, Kepler observations of G dwarfs are good, I think. And anything higher mass than that, again, you're good. So do you happen to know what the mass distribution of those companions looks like?
So at least in the AGGC, it's like, because of temperatures, it's right around 1 to 2. So it might be, in a sense, the thing I'm thinking is maybe we should cross-match to Kepler and see if there are things that are pulsating, because that gives us a lower bound on the masses, and things that are maybe below that we can start to pull out as lower mass companions. And then maybe look better, like look deeper in the features, because it is a big enough data set that if we slice 1,100 sources, you still have quite a few to make histograms with.
Yeah, I would be super interested in doing that project. Absolutely.
Cool.
Hit me up on Slack. We'll do that project.
Sounds good, Simon.
Some other questions? Anyone wants to try? Oh, yeah.
I have a question broadly about using astroseismology to probe the internal structure of stars that have experienced mass transfer, that have accreted material. So for context, in red giants, if they're rapidly rotating, it can suppress astroseismic signals. But I'm curious if that's also true in main sequence stars. And if it is, if you've spun up because of mass transfer, how long would you have to wait in order to detect any changes in your modes? Or like, would rotation suppress your modes? And if not, if it does, how long would you have to wait? And would those structural changes persist?
Yeah, but my model don't have rotation. I don't know.
Yeah, go ahead, Sandra. I'll jump in.
I don't know the answer for solar-like oscillators. So for GK dwarfs, I don't know what the answer is regarding rotation. As you move into the F dwarfs, they tend to rotate more quickly than the G dwarfs. Stars like Procyon you can do astroseismology on that star. Certainly for A stars, so the Delta Scuti stars that I was talking about, one of the things we're finding now with tests and with access to Gaia v broad data is that the more rapid rotators are more prone to pulsation. And so rotation definitely isn't killing anything there. You're all good there. Amadeus, can you say anything, or maybe Matthew can say something about more massive stars still?
Yeah, so regarding the higher masses, we me and Cole are on our way to get a project and to try to address those questions. How long after the spinning up due to the critical rotation, and how after that we have to actually wait in order to regain balance and thermal equilibrium in stars, and how it will actually impact our positional signal. But from the observational perspective, I have no idea.
Maybe I can say what I remember from my conversations with Dominic and other observers. But I think like in Ophiuchi, which is OE star and double parenthesis thing, so it's rotating crazy fast. Pulsations are seen, and rotation makes it. My understanding is that it makes it harder to identify the modes. So the analysis becomes much harder, and the question is, does it become impossible or not? That's what we are going to try with this new data. But in principle, it should not wash, at least for an O-type star like Ophiuchi. Observationally, it doesn't seem to wash out completely the pulsation. Actually, it might enhance them, but then identifying the modes, which is necessary to do this kind of analysis later, becomes much harder.
Yeah, that is certainly true. The more rapid rotators, mode identification is an absolute nightmare. But if you just wanted to do pulsation timing, from which you get all the same orbital parameters that you get from radial velocities, then it doesn't matter if your star is rapidly rotating. And in fact, it probably helps because the more rapid rotators pulsate in more modes, and so you win out in signal to noise by combining more modes.
So I have a question and a comment. So just going off what Katie was saying about question 1, I think that like incompleteness and selection biases are the kind of the most important thing holding us back there. Like we have all these different detection mechanisms and very few populations where everyone has applied those detection mechanisms to the same population. And that's really difficult to like get everybody on board to looking at like the same sample. My second question is just about, so you've been talking about delta Scuti pulsators and AF type stars. And I'm just wondering about selection effects there. Like, is it true that everything in the delta Scuti instability strip is pulsating? Or is it actually true that if you have had mass transfer and have like helium enrichment, or you've spun up the stars, that's actually exciting pulsations, and so you might have some selection bias there?
That is a fantastic question. I've worked on this a bit recently. In the Kepler sample, we find that something like 50 to 70% of stars in the instability strip pulsate, and that pulsator fraction is higher in the middle of the instability strip than it is near the edges. And that can quite easily be explained by, say, temperature uncertainties where, maybe some of the stars near the edge of the instability strip have been observationally blurred with stars that are outside the instability strip. When we look at clusters and associations, what we're finding is that the younger clusters and the younger associations have higher pulsator fractions. And so that would suggest that there is not an effect like mass systems that have had mass transfer that are dominating this pulsator fraction. On the other hand, we absolutely expect that stars that have received mass, they're going to have more helium near the surface in the zone that drives the pulsations, that helium-2 partial ionization zone. That's going to be more stocked with helium, and that will tend to drive pulsations more strongly. And so in that sense, mass transfer is a good thing. Yeah.
And actually also modifies where exactly does the star end up in HR diagram. So we have model predictions that not only stars inside the instability strip are actually able to give you some signals resembling delta Scutis or even gamma-Dor hybrids.
So I was also just wondering if you could kind of go over what we can do with the various sort of big missions, because I know like with Kepler, we had a longer baseline, so that sort of opens up what you can do astroseismically, what we can do with TESS. And then I keep asking people what we're going to be able to do with Plato, and I can't find a lot of people who know that much about what's going to happen with Plato. So if you guys could just kind of comment on that, or any other missions where you're expecting we're going to get sort of like large samples and we don't actually have to go over targets individually.
Simon, you want to comment on the observational part on Matthew?
Sure. So yeah, with Kepler, we had these 4-year-long light curves. That's excellent for the pulsation timing part because it's a bit like having a longer RV curve. The longer your curve is, the better you're going to parameterize these orbits. As far as astroseismology goes, in trying to detect modes and relate the observed mode frequencies to the model mode frequencies, we're finding that one sector of test data is adequate in this case. The more test sectors you get, you're slightly improving your signal to noise, and so you might find a few lower amplitude modes. But yeah, 27 days of data is actually pretty great for Delta Scuti stars. I haven't really heard much about Plato in this sense. I imagine it'll be TESS-like. And then Roman, I guess, is the other mission that's coming up that should deliver light curves for, I'm going to guess, well, tens of thousands of Delta Scuti stars. It'll probably be similar to TESS, right? So tens of thousands of Delta Scuti stars from Roman, I suspect.
And also, it's not that we are actually having difficulties getting some high quality observations for those stars. The main problem in terms of Delta Scutis is, well, if they're in binary systems that have like highly wide orbit, then we can use pulsation timings to extract radial velocities in some particular circumstances. But also the main problem for the other systems is actually the mode identification. And for that, we would need no more like high quality observations, but rather multicolor photometry or stuff dependent, like that, in order to actually get some reasonable mode identifications.
Yeah, so it might be interesting if Roman and Plato are observing the same targets in roughly at roughly the same time, and you can compare mode amplitudes across different passbands. That might actually help to identify pulsation modes. Maybe if TESS is still going at the same time, we'll get really lucky, but I'm not entirely sure what the various mission lifespans look like at the moment.
And also the pulsations in Delta Scutis are pretty stable, so maybe it's an option to use Kepler as some additional source as well. Yeah, we have another one. No.
Okay, there was a. No, I was thinking, do we want to maybe summarize some of the questions? I think we have like a little less than 10 minutes left. Is it a good idea to kind of go to some wrapping up?
Sure.
I'm not an expert, like, I don't know.
I'm not an expert in every question here, so someone, if you want to back me up, then I'll jump in for more like my relevant questions.
Do we have any responses to any of the questions?
Were you noting anything on the blackboard? No.
I guess we as we've discussed, like there are a few targets that we can immediately identify that have names, and we can find these products and try to analyze it. And from the theory side, both Amadeus' work, Tom's work, seems like astroseismology could be promising. There are lots of complications related to rotation, to the observed samples, but it seems a promising direction to me.
Yeah, it's also very hard to actually find any systematics in the observations that we're getting. So whether there will be possibly some solution with astroseismology to actually determine whether we are actually looking at pre-mass, post-mass transfer. So as for now, I don't know, it's like really hard to find any systematics. Yeah, so I don't know. Perhaps kind of a, well, some subset of hybrid pulsators may be an answer, but this is like also observationally biased, whether we are actually getting some high quality observations in order to actually be able to detect those hybrid pulsations or not.
I just want to make a comment about, or like in a more general way, like, or maybe focus on the number 3 question, like pros and cons of pulsations or astroseismology. Because like, I think modeling side, like for getting, let's say, eigenmodes or like pulsation frequency, that's pretty kind of help us to constrain the model. Because like, what's the eigenmode of a star, a given star, is very sensitive to its stellar structure. So that means like, okay, if we measured a bunch of pulsating frequencies, and it will very well constrain our model. Let's say, where's the radiative kinematic boundary? That's very, I mean, the excited wave, like, or the wave that we can observe, like very sensitive to like that bound. Because like also like for internal gravity wave, like G mode, it only propagate in the star's radiation. So like, yeah, so also like help us to see like the star have a bigger like radiative zone, or like, or where's those radiative zones. So right, so this is, I think, one sort of maybe like future aspect of astroseismology. Like if we have more like astroseismic eigenmodes measured, definitely like way better, like help us to constrain the inner structure. And also for, just remind for maybe people don't work on astroseismology, for helioseismology, people can like make model like very, very accurate, explain most of the modes. Or maybe I could be wrong. I mean, like my impression is that we have those like eigenmodes frequency measured, and the model can match the observation, let's say, several digit like after the decimal, so like that precise. So like I think will be like this whole like area will be a very promising like future of stellar evolution.
Just a quick comment regarding the observational sample. So one of, I mean, project I'm thinking that we have a clean sample of galactic 100, I think 100 BN star. So it's a stars just means they're rotating fast, but without any emission. So they're clean, I mean, sample also there looks like effectively single. And like what we want to do is just to go one by one for 100 star and just to make a frequency analysis with tests. And that's it, just to provide for theoretician like what we have. And we already thought that we have like two subgroups, like on this population. And I mean, they're just fast rotating B-type star, that's it. And I think so from empirical point of view, we do have like a bona fide sample. It's just no question of interpretation. So I hope, yeah, from empirical point of view, we will able to reach.
Yeah, and just like a comment for Meg's comment, we can also we have to also remember that all the time in theory we're relying on the theory that does not always account for various effects like winds, mass loss, and stuff like that, in regard as how it affects pulsations. And also, you brought up the helioseismology, which actually makes everything even worse because the more modes we have to, we have in order to match them and fit in our observation and model cross checks, the more those uncertainties will be piling up, making our models like less, maybe not efficient, but accurate.
If I can jump in an attempt to sort of wrap up, I think, yeah, there's a lot of promise in using astroseismology to constrain models. Like you get really good stellar densities, cosmology in particular. But when you introduce binarity and mass transfer, you're introducing so many free parameters, right? So, when did mass transfer begin? How much mass was transferred? What was the rate of mass transfer? How is that transferred mass distributed through the star? How does that depend on other stellar parameters such as rotation, which can mix the bulk material within the star? And how does it depend on things like the efficiency of overshooting from A, the convective core, and B, beneath the convective envelope, if there is one? And so there are various parameters that we're not even particularly constraining very well for single stars. And if you're adding binarity to that, you've really got your work cut out in terms of a giant parameter space that you somehow have to navigate. I think that's what Amadeusz is saying, in the sense of you're trying to maintain accuracy in your models, but you've just got so many parameters. And so I can't stress enough the importance of observational constraints here. You really need everything that you can get.